Hello everyone, welcome to my third video on the existence theorems. So the last but certainly not least theorem that we're going to look at is the mean value theorem. In my opinion, the mean value theorem is one of the most underrated theorems that we have. This one is super strong. It's extremely important. It single-handedly opened up its own branch of mathematics called dynamical systems, and it's all based off this theorem, the mean value theorem. So let's take a look. So it states that suppose that f of x is continuous on a closed interval ab. So again, we have continuity on a closed interval ab, and it's differentiable on ab, on the open interval ab. So we have continuity on the closed interval, differentiability, we could take its derivative on the open interval ab. If we have these two conditions, which is similar to Rolle's theorem's third statement required f of a to be equal to f of b. We needed that. Mean value theorem, we don't need that anymore. Then there exists a c in the open interval ab such that f prime of c equals f of b minus f of a divided by b minus a. So this has to be memorized. So I'm not going to prove it. The proof is it's a bit long, but not overly complicated. I'm going to skip it and just provide you with the idea. So the idea is the following. We have our y-axis, our x-axis. Let's go ahead and sketch the function. So we have some point here, a, b, it could be anywhere. Let's put it up here. And let's say we have, I don't know, again, some function that looks like this. So we don't need f of a to be equal to f of b. This is f of a. F of b is up here. So we have this function here. What the mean value theorem is saying is that f prime of c, it's the derivative, we think of this as the slope of a tangent line. And f of b minus f of a divided by b minus a, we've seen this already. This is essentially just y2 minus y1 divided by x2 minus x1. It's the slope of a secant line, okay? Just the equation of a line, the slope of a line. Slope of a secant line. So what the mean value theorem is essentially saying the same thing, it's essentially saying the same thing that Rolle's theorem told us. But Rolle's theorem put it horizontally, where f of b had to equal f of a. Mean value theorem is the exact same idea, but just slanted. It's basically a tilted version of Rolle's theorem, and it's saying that if we connect a and b with a line, this is the slope of our secant line. Let's do this one in black. So the slope of the secant line is in black, connecting a and b. We have this line here. It's saying that there exists another point in between a and b, at least one, doesn't have to be only one, it can be at multiple places, in between a and b, where the slope of the secant line matches the slope of the tangent line. So if we look at this value up here, let's say, doesn't necessarily have to be the max, let's call this C1, the slope of the tangent line is parallel to the slope of the secant line. I didn't draw it properly, but this you should imagine is parallel to the slope of the secant. The slope of the tangent is parallel to the slope of the secant at C1. And this occurs also at this point here. Let's call this value C2. Notice that C2, if we take the slope of the tangent, it's parallel to this line, which is parallel to this one. Okay, and this is the idea of the mean value theorem. It's telling us that at some point C, could be multiple C's, it's the derivative, the slope of the tangent, is equal to the slope of the secant line. That's the observation that's made. Let's go ahead and look at a couple examples. So in this example over here, we have to find the slope of the secant line when x1 equals 0 and x2 equals 2, given the function f of x equals x cubed minus x squared minus 3x minus 5. And then we have to find the value x equal to c on the interval from 0 to 2, where f prime of c equals the slope of the secant line. So let's go ahead and do that. So what do we begin with? First of all, we're applying the mean value theorem, so we need two things. We need continuity on a closed interval, and we need differentiability on the open interval. Is this function that we're given continuous? Well, yes. We're dealing with a polynomial, and we know polynomial functions are continuous. And are they differentiable? Can we take the derivative of a polynomial function? Again, yes. So there's no issues there. We could apply the mean value theorem. So let's go ahead and do that. Let's begin by finding the slope of the secant line. We know that the interval is 0 to 2. You can think of this as your a value. You can think of this as your b value. So the slope of the secant is equal to f of b minus f of a over b minus a. F of b is f of 2 minus f of a, which is 0, over 2 minus 0. Okay. So let's go ahead and find our f of 2 and f of 0. So we're just going to plug it into the function. F of 2, it's equal to 2 cubed minus 2 squared minus 3 times 2 minus 5, giving us 8 minus 4 minus 6 minus 5. What is this? 4 minus 6 is minus 2 minus 5 is negative 7. And then we have to find f of 0, which is 0 cubed minus 0 squared minus 3 times 0 minus 5, which gives us minus 5. Okay, so we found our f of 2, f of 0. Let's plug it into our equation here. We get minus 7. F of 2 is minus 7 minus negative 5. Be careful with your negatives. And 2 minus 0. Negative 7 minus negative 5. Two negatives here make a positive, giving us plus 5. So this gives us negative 2 on the top and positive 2 on the bottom, giving us negative 1. So the slope of the secant line is negative 1. That's the first part. We finished this part over here. Second part is asking us to find the value c on the interval 0, 2, where f prime of c equals the secant line. Let's go ahead and do that. So we know the slope of the secant line, I'm just going to erase this, is negative 1. So that's done. And we know the equation of line for the mean value theorem, well, not the equation of line, but the equation for the mean value theorem is f prime of c equals f of b minus f of a over b minus a, which we just solved. This is equal to negative 1. So really what we have is f prime of c is equal to negative 1. So our job is to find the value of c. So what we have to do is take the derivative of this function. So taking the derivative of f of x gives us 3x squared minus 2x minus 3. Okay, so this is the equation that we have. So we found f prime of x, but here we want f prime of c. So essentially the equation that we have, we're going to replace the x's here with c's. So this gives us 3c squared minus 2c minus 3 equals negative 1. This is the equation we want to solve. So it's essentially just a quadratic. So we can bring over the negative 1. We get 3c squared minus 2c. Add 1 over, you get minus 2 equals 0. And now here you can use the quadratic equation, or you could use the factoring method. I would prefer you use factoring method. So let's go ahead and factor product sum. You're multiplying two numbers to give you a times c, which is negative 6. And adding two numbers, the same two numbers, to give you your b, which is negative 2. So what two numbers multiply to give you negative 6, but then add to give negative 2? Well, the factors of negative 6 are 3 and 2, or 5 and 1. Sorry, or 6 and 1. So these don't work. So you have to use the quadratic formula. So factoring, unfortunately, in this case doesn't work. We're stuck using quadratic. So for the quadratic, what we have is c1 and 2 minus b plus minus square root of b squared minus 4ac over 2a. So minus b is negative 2, so negative of negative 2 becomes positive 2, plus minus the square root b squared, so negative 2 squared is 4, minus 4 times a, which is 3, times c, which is negative 2. All that over 2a, which is 2 times 3, which is 6. This gives us 12, negative 24, positive 24 plus 4 is 28. So 2 plus minus the square root of 28 over 6. Okay. Let me plug this into a calculator. Plugging this into a calculator, we get square root of 28 plus 2 divided by 6. We get C1 equals about 1.215, and C2 gives us about 2 minus square root of 28 divided by 6, negative 0.55, let's say. Using quadratic formula, we get these two answers, and we're not done. So we're looking for the values of c that lie in this interval. So in this case, we got two answers. We got c1 equals 1.215, c2 equals negative 0.55. We have to take values that are in between 0 and 2. That's the interval for which we're looking for, the c values that fall within 0 and 2. So we have to reject the negative 0.55. So at the end of the day, the c value that satisfies this equation is just the 1.215. This is the answer, and we're done. So it's at this value here, c1, 1.215, where the slope of the tangent line matches the slope of the secant line. So in this example here, we have to consider the function f of x equals tan of x, and show that f of 0 equals f of pi. But at the same time, show that there does not exist a c in this interval from 0 to pi such that the derivative at this value is equal to 0. Okay, and we're going to look at why doesn't this contradict Rolle's theorem. So we're stepping back to Rolle's theorem. Why doesn't this contradict Rolle's theorem? So remember, Rolle's theorem states that if f is continuous on a closed interval ab, f is differentiable on an open interval ab, and f of a equals f of b. If we have all these three things, then we have f prime of c is equal to 0. This is what Rolle's theorem essentially tells us. Continuity, differentiability, f of a equals f of b, then there's a point in between a and b. Then this is true for c in between a and b. Open interval a, b. Okay, so this is essentially what Rolle's theorem is telling us. Why doesn't this contradict this statement? So let's go ahead and show first of all that this is satisfied. Show that f of 0 equals f of pi. So f of 0, the function we're working with is tan, so tan of 0 we all know is just 0. And then what's tan of pi? Well, to answer that, if you're not sure, without the use of a calculator, use your unit circle, replace tan with sine over cos, and what we get is sine of pi is 0, cos of pi is negative 1, so this is just 0. So we showed that f of 0 is equal to f of pi, they're both equal to 0. So we have this third condition that's satisfied. Great. Show that there does not exist. So this is a backwards e is there exists, with a line going through it means there does not exist. So there does not exist a c in the interval from 0 to pi such that the derivative is equal to 0. So if we take the derivative of tan, f of x equals tan of x, the derivative f prime of x is secant squared, and there does not, between 0 and pi, there's no situation where this is equal to 0. There's no value of x that you could put in here to give it equal to 0. Secant is 1 over cos squared. And no matter what x value we put in here, cos can't be 0 because you're going to essentially be dividing by 0, so there's an issue here. Why does this not contradict Rolle's theorem? So we don't have an issue, there's no situation where the derivative could be equal to 0. But Rolle's theorem says there has to exist a c where the derivative is equal to 0. So what's going on here? We took the derivative, so we have differentiability. What you have to catch is the fact that tan of x, if you sketch it, let's quickly sketch the tan function. Tan has asymptotes, negative pi over 2 and pi over 2. It's periodic, so it repeats, and it looks something like, let's do it in green. It looks something like this. So we showed at 0, this is the y-axis, This is the x-axis. We showed at 0, this value here, it matches, let's extend this. The next periodic function here, this is going to be pi. At 0, it's 0, here it's pi. But there's no place where the derivative is 0. But could you see the issue with this? We have an asymptote in between 0 to pi. So the condition that's missing here is the first one, continuity. We do not have continuity. The function here goes to infinity, but then I have to lift my finger to come back here and continue from 0 to pi. So the function's not continuous. That's why this doesn't contradict Rolle's theorem, because the function that you're dealing with is not continuous. So in order to apply Rolle's theorem, it's really important that you catch that we have continuity, differentiability, and f of a equal to f of b. If those three conditions are satisfied, then we could use Rolle's theorem. Okay, so watch out for that. So in this example over here, it says to consider the function f of x equals 2 minus the absolute value of x minus 1. It says show that there does not exist a c in the interval 0 to 2 such that f of 2 minus f of 0 equals f prime of c times 2 minus 0. And explain why this does not contradict our mean value theorem, MVT. Okay. So let's begin with this. F of 2 minus f of 0. Let's plug in 2 into the function. We have 2 minus absolute value 2 minus 1, which is 2 minus 1 is just 1, and absolute value it stays positive, so it's 2 minus 1, which is 1. And f of 0 is equal to 2 minus 0 minus 1, which is equal to 2 minus 0 minus 1 is negative 1. In absolute value it turns it to positive, so it becomes positive 1. So 2 minus 1, which equals, again, 1. What we get here is 1 minus 1. So f of 2 minus f of 0 is just 1 minus 1, which is 0. So 0 equals f prime of c times 2 minus 0, which is just 2. Divide both sides by 2, we get 0 equals f prime of c. So why can't the derivative equal 0? What's the issue with this? Well, what you have to catch is that in order to apply a mean value theorem, the function that you're dealing with has to be continuous, differentiable, and this is mean value theorem, not Rolle's theorem. It has to be continuous and differentiable. We have continuity. It's an absolute value function, which is continuous. It's just a v. But do we have differentiability on the interval from 0 to 2? No, we do not. If we sketch this, we get a function that looks like this. 2 minus x minus 1. So if we plug in 0, you get negative 1, positive 1. Add 0, you get 1. If you plug in 1, you get 2. If you plug in 2 minus 1 is 1, you get 1. So you get like a v that looks like this. Something like that. And notice that you get a corner or a curve, which means that there's no tangent here. Over here, notice at this point here, you could have multiple tangents. It hits the corner at that one point. So whenever you have a corner, we know it's not differentiable, the function, so it fails the property of differentiability. We can't take the derivative of absolute value function. So for that reason, mean value theorem does not apply. So ensure when you're using mean value theorem, any of your existence theorems, that your continuity is satisfied and differentiability is satisfied in this case. Okay. So in this next example, we have if f of 1 equals 8 and f prime of x is greater or equal to 4 for x values in between the interval 1 and 3, then how small can f of 3 be? So let's go ahead and do that. So in order to apply this, we need to use the mean value theorem. So this is MVT. So we start off by plugging in the problem. It's not given in the problem, but it should be stated that f is continuous and differentiable. Its derivative exists. F prime of x is greater or equal to 4. So let's go ahead and write our formula. We know that f prime of c equals f of b minus f of a over b minus a. And we're given the interval. So we have our a and we have our b. A is 1, b is 3. And we know that f prime of c, and c is going to lie in this interval as well, has to be greater or equal to 4. So if this is equal to your f prime of x, it has to be greater or equal to 4. That's telling us that this whole thing has to be greater or equal to 4 as well. Okay, so f prime of c, which is equal to this, has to be greater or equal to 4. So let's go ahead and solve for f of 3. F of b is really just f of 3. Okay, so it's important to understand f prime of c, the derivative is going to be greater or equal to 4. Well, if the derivative is equal to this, then this thing has to be greater or equal to 4. That's the argument that we're making. F of b, b is replaced with 3, a is replaced with 1 minus f of 1 over b minus a, which is 3 minus 1, and this thing is greater or equal to 4. So we're looking for f of 3, and we know f of 1 is equal to 8. So we have f of 3 minus 8 divided by 3 minus 1 is 2 is greater or equal to 4. At this stage here, we're going to multiply both sides by 2. Since we're multiplying by a positive value, it doesn't affect the inequality sign. Remember, if you're multiplying or dividing by a negative value, your inequality sign flips. So be careful for that. So we're going to multiply both sides by 2. It's positive, so we're fine. We get f of 3 minus 8 has to be greater or equal to 8. And then we're going to bring the negative 8 over, and we add 8 on both sides, giving us f of 3 has to be greater or equal to 16. Okay, so the smallest value of f of 3 would be 16, and we're done. So this is an example of an application of mean value theorem. So I hope this helped. I hope you enjoyed the video. So keep practicing, and I'll see you in the next one.